It's my pleasure now to introduce Larry Kahn. Larry Kahn is from Georgia Tech, and Larry is going to be talking about reinforcement section loss and structural repairs.
On structural repair of corroded reinforcement, this really came to Committee 364 as the question, how should I deal with corroded reinforcement, and should I be concerned if the loss of section is less than 10%? Well, Ron Heffern and I were assigned, and this is the work of, again, Committee 364 is FAQ. So we started investigating this, and the significance is obviously that the quality of reinforcement is fundamental to the strength of reinforced concrete structures. Whether additional or replacement reinforcement is needed is always of a primary concern to rehabilitation, because flexural strength is directly dependent upon the area of reinforcement, and same with shear strength and the like. And we know we have problems in corrosion when we see a structure like this. On the other hand, most of the times we're seeing corrosion when we're just seeing some rust stains on the outside of the concrete, some minor cracking and the like. So the first job is, we know we have some kind of corroded reinforcement, is to examine that reinforcement and the quality of concrete around it. And that is, we have some of the concrete removed and see how well the bar is bonded. And so we chip hammer out some of the material down to very solid concrete. Sometimes we only can see rust above the mid-height, in which case you may not need to chip down lower than that. On the other hand, with weakened concrete or rust surrounding the reinforcing bar, you have to chip all the ways around. Then down below the bottom of the steel, a minimum of 1/4 inch plus the maximum size aggregate, and generally my recommendation is 1 inch, and I think that's what our committee is coming up with. So to get enough room under there to actually inspect the bar and to be able to clean it, which is the primary thing. You have to be able to clean that bar thoroughly all the ways around. Then you have to measure the reinforcement, and this isn't easy. I suggest wire brushing. You can sandblast or shot blast using appropriate environmental concerns. Water blast if you're an exterior environment to a bright surface. In cleaning the bars, generally don't recommend you're using solvents, because solvents can act as a grease and not allow new surrounding materials to bond well with the existing concrete. So solvents are generally not a good idea. If the bars are epoxy coated, you should expose a broad area around where you see the rust products, because it can be rusting underneath places where you have the epoxy coating. And then you have to measure it. And I suggest measure the smallest sections, with calipers in all directions so you can get kind of an average diameter. In researching this, there's not a standard for reinforcing bars. There's a standard for size. That is, if you say you have a number 9 bar, which is now called the number 25 bar, that it has 1.0 square inches of steel. But in order to get that, there is, even if you read ASTM for the A615 steel and others, you can have different size deformations, different deformation patterns, different amounts of steel in the rib deformation compared to the body of the bar, as long as there's 1 square inch. So finding an actual area is a difficult thing. Even finding the area within 10%, that itself is difficult. So don't be surprised if there's trouble finding areas. So we're suggesting taking the easiest, smallest measure to have a conservative measure of how much steel is left. Then, the consequence of a 10% loss. Say you measure the bar, yes, you have, only 90 or 80% of the bar remaining from your computations. Well, the first and nicest thing to do is to take measurements of the entire structure, because you're evaluating for rehabilitation. In the standard building code, ACI 318 document, chapter 20 for existing structures, if you know the dimensions of the section, and you have a very good idea of what the concrete strength is by test, and you know what the yield stress of the reinforcement is, then the flexural factor, capacity reduction factor phi, you can take that as 1. that automatically has given you the 10% increase in strength that you think you may need based upon computations. So that's the easiest way that 10% is not going to matter for you. You can also consider moment redistribution. If your reinforcement, and this is for flexural design, is corroded in the negative moment regions, whether columns or flexural members, you can distribute that negative moment to positive moment areas that may not be corroded up to about 20%. Now, it depends upon the ductility of the section, your reinforcement ratio compared to the balanced reinforcement ratio and the like. But this is an analytical technique that generally you can distribute 10% at least of the negative moment capacity over to an uncorroded positive moment section and not have to do any more than just clean the reinforcement. The next and typical item is that in most designs you've provided, or the designer has provided, actually more reinforcement than was required by analysis, because we have to put in a given number of reinforcing bars, and generally the designer did not put in the precise area required by analysis, but it became something more than analysis required. So you just compare this ratio of AS provided to AS required. In all of those, you typically will have your 10%. But I think the most important thing that I've seen in my investigations has been the location of the corroded reinforcement. So if we take a look at, let's say, the horizontal frame members in a frame, flexural steel, and we have some kind of moment envelope from what our anticipated loads are, the red zones is where I say we should be really concerned. The yellow zones are probably where we're not concerned. So as an example, if we look at on the left-hand side, the top negative moment reinforcement where we have the highest moments, that is where you really do need to be concerned for measurements. On the other hand, if you take that same bar and go out into the positive moment region where all you've done is have development of that negative moment reinforcement, but you have the same area, you could have a very substantial loss of reinforcement that you don't need to add any bars to, because we only need the actual area of steel to resist the forces in the bar. That is, officially that bar could be tapered down to a 0 point, right, in order to have it developed within the section. So if it's at a section where we truly don't need it, then you don't need the bar. Right? You can do with a very much reduced section. Same with a positive moment reinforcement in the bottom, and let's say the negative moment region. Some steel needs to be there for continuity reinforcement in section 7.12, but if it's not needed for such continuity reinforcement, again, you don't need to be concerned about its replacement. Shear reinforcement, the same thing. Generally in high shear regions, the designer has only put in enough shear reinforcement that he needs, and you may have to add some replacement. On the other hand, I've seen some vertical steel continue throughout the cross-section where it is not needed in the middle part of a flexural member. It may not be needed. One has to actually look at the shear envelopes, but where the vertical steel has been placed in order to hold up the horizontal reinforcement. That is, it's been a chair. The horizontal reinforcement already being there is held up by the remaining concrete. Those vertical steel bars are no longer needed. So again, that may not be of a concern. Columns, the same way. You have to look at the moment axial load envelopes. Typically, the axial load can be handled by the strength of the concrete that's there. In many columns, the concrete strength is much higher than the strength required, and so the steel is doing less axial load, is much less responsible for axial load responsibility, but it is still dramatically needed for lateral load or flexural capacities. So in your analysis, you just have to determine how much flexural capacity the column actually needs. So in effect, you're getting around a lot of corrosion problems by doing the detailed analysis of the structure. In seismic considerations, which now through the International Building Code, even the folks like me in Georgia, we are highly concerned about seismic actions because in the last 2 months our seismic requirements have increased dramatically. But in FEMA and NEHRP guidelines, where you can look at an existing lifetime of a structure, you can use lower seismic criteria if you designate a shorter lifetime for the facility. So the same thing for then replacing reinforcing steel, you can also look at the extended lifetime of the structure, right, in order to see what your seismic design criteria has to be. Finally then in repair, if we've chipped out concrete, and the yellow bar with the black is where I'm showing some corrosion products, the green is some kind of replacement steel. One of the easiest things to do is to chip out really good concrete so that you have enough development length so that you can lap splice the bars for development. Remembering that the only steel you need to add is to get back to existing capacity, and therefore the development length is for the shorter or smaller diameter reinforcing steel. It's not the development length for the large bars that were originally there. You also have to consider cover requirements here. By putting the bar, like I showed, the green bar on top, you reduce the cover for that bar. That's not a good thing. You really want that green bar horizontal or at the same level as the yellow steel. That oftentimes means chipping out some good concrete so that you can place that bar. The next is, yes, you can weld the reinforcing bars together. This gets controversial, but you can use that flare bevel weld. According to American Welding Society, welding code for reinforcing bars, D1.4. Now, in doing that, some guidelines that I've learned, I've read these D1.4 several times, and this is where you do need your chemist to help, is the main thing you need to know is the carbon equivalent content of the reinforcing bars. You actually only need a small scraping of the good part of the bar for a chemist to be able to tell you that. If it's over around 0.75%, then you're in trouble. But most bars since World War II have a smaller carbon equivalent content than that, and therefore they are weldable given you preheat up to around 300 degrees Fahrenheit. Now, preheating reinforcing bars in reinforced concrete is a difficult thing because the concrete is a fantastic heat sink and will just sap a lot of heat away. But heating up to those low levels is certainly very possible to do as long as a welder is experienced in welding and, preheating rebars and welding. On the other hand, reinforcing bars prior to the 1920s typically have such a high equivalent carbon content that they are not weldable. Where you really need the chemistry analysis is for buildings built during the 1930s, early 1940s, where you oftentimes don't know what the quality of iron or steel is in that steel bars, and where welding can be really controversial. Mechanical connectors are possible, although I have never seen them used, for this kind of application. What I've done sometimes, though, is use just a 36 steel angle iron, and that's really easy to put in, and to have a flare bevel groove weld to that, and use that angle iron rather than a lap splice reinforcing bar in order to make connections. So there's another possibility, and you can think of many, many more. We had just heard about this halo effect. Certainly, in looking at the patch material, once you have the new reinforcing steel in there that's been welded or onto the old steel, and you have this non-contaminated material that you place as the patch material, that repair has now become a cathode. The area just around the new patch now becomes the anode, and you can certainly initiate corrosion in that new anode. For this, you need to read the rest of Committee 364 documents, 546, contact Alex Faisberg, all the rest, for what materials you should use, and if you should use some type of cathodic protection, or you can talk to other individuals about the possibility of even considering using corrosion inhibitors, right, or whatever. But other considerations is also the use of external reinforcing. That is, yes, you have rusted reinforcing bars, you put a patch in, but then you use external reinforcing. It could be pre-stressing, it could be fiber reinforced polymer bars or strips, as per some new documents from ACI Committee 440, that is FRP reinforcing. Another consideration is shoring. If you have horizontal elements or vertical elements and you're welding those reinforcing bars, you really have to be concerned, because once the yield stress of the reinforcing bar will be about 1/2 its capacity when the bar reaches 900 degrees Fahrenheit, and it will reach that when you're welding on it. Therefore, your capacity of the structure can be dramatically reduced if you only have 2 reinforcing bars present. You're welding on one of them, you have a much reduced capacity. If you have dozens of reinforcing bars, you're welding on one of them, you don't need shoring. So just be very concerned about shoring needs. And the last issue, which could be the controversial one, is jacking to remove dead load stresses. Typically, I think in most repairs, I believe jacking is not necessary, because the ultimate strength capability of the structure is going to rely on the yield capacity of the existing reinforcement plus your new reinforcement. And at ultimate, given that your structure has enough ductility, that is, your reinforcement ratio is significantly less than the balanced reinforcement ratio, it can deflect such that all the reinforcement will be yielding. On the other hand, if the structure is totally dominated by dead loads, the serviceability may be enhanced if the dead load is removed, that is, the structure is jacked prior to adding new reinforcement. So this is a real structural engineering concern, is the relationship of dead load to total load stresses and whether you need to jack or not. And I think that's individual for each particular project. I left time, so if this is controversial, y'all can ask lots of questions. No, not controversial. Oh my goodness.
One of the problems an owner has is the question you just put up before us. Once you have the differential materials situation after the repair, and then what do you recommend? I'm asking you. That's what faces us as an engineer. I'm not going to go to a material supplier because I can't understand what they're saying. They give me all sorts of competing data. And so what are you, as a consulting engineer, going to recommend to be done to provide the most cost-beneficial repair in that situation?
Okay, as a consulting engineer, the first thing I'm doing is having you sign this great contract with me. But that's a joke, that's a joke. Thank you, Clyde. First of all, that's a serious issue, and I will dance around here some. The first thing to say is every job is individual. And so you as an owner have to understand that a lot of investigation is going to have to be done for your particular job. There's not a general solution. With regard to stopping corrosion of reinforcement around, that halo effect, is that the question you're asking?
Yeah, I'm talking about what I call the donut effect.
Right. Other people call it halo effect, but basically it's creating new anodes, a new place, chasing the anodes around the structure, as the previous speaker said. I've seen some things work and a lot of things not work. And in press current, I've seen being a good answer, because I've seen that work in marine structures and work very effectively. It's an extremely expensive technique. In most cases...
You're talking about cathodic protection?
Yeah, but in press current cathodic protection. That is, you're hooking up, electrical lines all over the place to the structure and determining if that's continuous. I think that works the best, but it's actually the most expensive. Some data that I've seen on fairly porous concrete, these little pucks seem to work from research data I've seen. You can see it in the exhibit hall where you put little zinc anode pucks in the new material, and that forms a better anode that wants to corrode rather than the steel corroding, right? So I might recommend putting that in. The surface applied corrosion inhibitors, if you're willing to be a research site, then I think it's good to put on. There are some studies that show it works as well as has been presented. There's some studies that have shown it hasn't done anything to benefit the client, and you think you're buying something that's going to be good and it doesn't do any good. Some cases it got worse, right, what Alex said. I've seen it remain the same. I've read a lot of literature recently on it. It's up in the air. I think probably the better thing to do is to uncover as much area as you can afford as possible to get rid of contaminated material and passivate, the reinforcement by putting in new good materials. But that does mean that you're removing material that you think is good, but may be highly contaminated.
Thank you.
That will bring up more controversy, I hope.
2 points. Paul St. John, consultant, 31 years with the New York State Department of Transportation, fixing many, many, many thousands of bridges. I highly concur with your assessment. We have done this over and over and over again, where we've lap spliced the bars. Cutting them and welding them, you just set up another corrosion cell. I don't care how you cut it, you started another corrosion cell. But to answer this gentleman's question, and again, your presentation was right on the money. We've done it on hundreds and hundreds of bridges, actually thousands of bridges. It's worked very well. Get rid of as much material, lap splice it as close as you can. Migrating corrosion inhibitors, there are 3, and only 3 that I found. And there's another gentleman here who did an NCHRP study. I won't mention his name. He's sitting right to my right. And there's only 3 that really worked. And what we found is if you use those 3 and you complex up what's left in it, and I did a bridge for IBM this year and did it exactly the same way, and you put in a good dense material that's in there, and you now say, okay, I'm done. No, you're not. Put 2 coats of silane sealer on it and keep the rest of this ring corrosion stuff away. The New York State Department of Transportation does every single bridge. Our maintenance department does the old bridges, and voila, we're going to save in 40 years $20 billion by doing this, because that's what our research has shown. So if you want to stop corrosion, you got to stop some of the elements that are going to cause it. Keep the water and salt out, make good decisions on how you do the repairs, and you're right on the money. Thank you.
Thank you. Thanks. No, that's right.
Do we have time for more questions for Larry before we move on? No?
Good.
Okay.
Thanks, Larry.